Hello and welcome to the lectures on state space approach to control system analysis and design. The topic which we are going to study now is LYPUNOV'S stability. Today in this video I will give some introduction to stability and thereafter, before actually we come to the topic of LYPUNOV'S stability, I will give some introduction to those mathematical concepts. We will recall those few mathematical concepts which will be useful in understanding the LYPUNOV'S stability. It may be a refresher for some people who have already studied these mathematical concepts, who are aware about it. However, for some other people who have not studied it, it will provide as a sufficient information to understand LYPUNOV'S stability. Now, we have covered mathematical modeling of dynamic systems, and we have done time response analysis. We solved the mathematical equations using the state transition matrix, or we also saw how we can use numerical methods to solve the state equations. Now, either through STM or through numerical methods, when we determine the time response solution of the state equations, we explore the system behavior for our own understanding as well as for the assessment of the system behavior, evaluation of the performance characteristics like transient response, steady state response, etc. By doing that, we gather a lot of information, and this is probably the maximum information that can be obtained about a system. We studied controllability and observability. They are new to the modern control systems, and the controllability gives a guarantee for designing a control such that the system will have the required transient response characteristics, transient behavior. Observability gives a guarantee that the states of the system can be determined based upon a finite record of output and the input. So both these, they are essential to controller design and the observer and estimator design. Stability is something which is very significant. It is a property by virtue of which a system returns back to its initial equilibrium, or it achieves a new equilibrium past an input disturbance, past a change in the input. So this property is again very important, because unless the system is stable in its operation, it may not probably serve the purpose. A system not designed for stability is rarely found. So that is why we will understand stability, and even though we have seen stability from other viewpoints, the motto here, the objective here is to understand stability in the sense of LYPUNOV. So as we know, there are several definitions of stability. The most important ones I have listed here: the bounded input, bounded output stability, which suggests that if a system is given a bounded input and in response its output is bounded, then the system will be stable. We can also define stability based upon the impulse response. If integral of impulse response from 0 to infinity is finite, then the system is treated as stable. So we have a definition based on impulse response. Then we can obtain the poles by solving the roots of the characteristic equation, and if the poles are situated in the left half S plane, or if the poles have negative real parts, then we call the system as stable. We also obtain eigenvalues by solving the eigenvector equation of of system matrix, and thereby we get the location of eigenvalues. If they have negative real parts, then the system will be stable. Now we also know a few methods in the undergraduate program in the control system subject. One comes across this Routh-Hurwitz stability criterion, which doesn't give exact location of the poles of the system, but it tells how many poles are in the left half S-plane, how many in the right half S-plane, are there any poles on the imaginary axis, based on which we can derive the stability information. We have come across in the undergraduate program the Bode plot, Nyquist plot, and the criterion based on these two frequency response techniques to know the stability information about the system. We also know the root locus technique, in which by varying a system parameter, most commonly the gain, we decide the good location of roots, or also we assess the stability of the system. So there are a few methods for stability analysis, but as I said in the beginning, the objective here is to learn stability in the sense of Lyapunov, the Lyapunov's stability, and it provides as a significant foundation for understanding control design concepts in modern control. So for example, in optimal control, adaptive control, sliding mode control, etc., we will often face a particular form of Lyapunov equations, which I will tell in these lectures. So as I said, we are going to first cover a few mathematical concepts essential for understanding the Lyapunov's stability. And among them, the first is the definiteness of a scalar function of a variable. So given a variable x and its scalar function fx and an interval between a and b, both the ends included, x less than equal to greater than equal to a, or and less than equal to b. So the function defined over this will be called positive definite if the function values are greater than 0 on this interval. It will be called as positive semi-definite if, besides being positive, some values are also 0. So the function will have some values positive, some values 0 over this interval. Then the function will be called positive semi-definite. And when it was only greater than 0, then it was being called positive definite. We will call the function as negative definite if the values of function are 0 over the interval, everywhere over the interval if the function is 0. We will call it negative semi-definite if, besides being negative, it will be 0 at some locations. So if it is strictly negative at all locations, then it will be negative definite, and if it is also 0 at some locations, then it will be called as negative semi-definite. And if the function doesn't fall into any of these categories, if it can acquire positive values, if it can acquire negative values, or it may become 0 somewhere in the interval, then the function will be called as indefinite function. It is neither positive nor positive semi-definite, nor negative semi-definite. It is indefinite. We have a concept of spherical region. We have come across this definition of norm, which is called as Euclidean norm of a vector x, and if this norm is less than equal to k, then this denotes a spherical region about the origin in the state space. So in a two-dimensional space it will be a circle, in a three-dimensional space it will be a sphere, which we have studied, and in a space of dimension more than 3 it is called as a hypersphere, but the general terminology we are using here is a sphere. So norm x less than equal to k is a spherical region in the state space, and this, of course, this norm we are defining is the Euclidean norm. So with that, and after having understood the scalar function of a single variable, we will understand the scalar function of a vector x better. So we denote a scalar function of a vector by Vx, and we are defining it over a spherical region. Inside the spherical region, norm x less than equal to k. The region I defined already here. So this function of a vector x will be called as positive definite if its values everywhere for non-zero x are positive, and at the origin of the state space if its value is 0. So two conditions. One is that V0 is 0, at the origin of the state space it is 0, and everywhere else in the sphere it is positive. Then the function will be called as positive definite. If its values everywhere is negative, all values are negative for non-zero x, and at the origin of the state space it is 0, then this function will be called as negative definite. So if positive for x not equal to 0, then positive definite. If negative for x not equal to 0, then negative definite. And positive semi-definite if at some places, some locations, it may be 0 also. So for the different values of x other than v0, other than at x equal to 0, if the function can acquire both positive and 0 values, it will be called as positive semi-definite, this one. Similarly, if it can acquire some negative values and some 0 values, and if v0 is 0, then it will be called as negative semi-definite. These words are the word to be taken into cognizance. So in this way we define Vx, the function of a vector x, and the region we consider is this spherical region. So these values of x we have considered in the spherical region, norm x less than equal to k. If the function doesn't fall into any of these categories, if it is neither positive definite nor negative definite, nor positive semi-definite nor negative semi-definite, then the function will be called as indefinite. So after working out these only, we will be able to know whether the function is indefinite or not. But anyway, we don't have to decide about indefinite characteristics. We have to find out whether the function behaves in any of these categories, mostly positive definite, positive semi-definite, negative definite and negative semi-definite. These are the things we look for among the properties required for LYPUNOV'S stability about a function having vector x as the argument. We move further. So if this k is very large, that means the spherical region is larger and larger, then we call these definitions as global, because they hold good everywhere. They hold good in a infinite region. So these definitions are called as global definitions. So some examples to understand the positive definite, negative definite functions, etc. We consider this Vx first, which is same as the Euclidean that norm we saw. It is sum of squares of the values along various coordinates. So x1 square plus x2 square, etc. up to xn square. We see that it is squares. So whether x1 is positive or negative, x1 square will be positive. Similarly, x2 square will be positive irrespective of positive or negative values of x2 and so on. And this is sum of the squares. So sum of the squares will also be positive. And we also note that if all x1, x2 up to xn, if all are 0, that means if x equal to 0, then Vx will be 0. So this function satisfies the properties of being positive definite. We call it positive definite. This function, which is in an n-dimensional space greater than 2, it is sum of the square of x1 and x2. And other terms are missing. So that means it is x1 square plus x2 square plus 0 times x3 square and so on up to xn square. So what we see that for positive and negative values of x1 and x2, this term will always be positive. However, if x1 and x2 alone are 0 and x3 etc. they are non-zero, then also this function will be 0 because of this. So we see that this function satisfies the properties of being positive semi-definite. We see another example. If it is square of sum of values x1, x2 etc. up to xn, then we can see that if x1, x2 etc. all are 0, then this Vx is 0. So V0 is 0, that is satisfied. But this summation may be 0 for some x, some x1, x2 etc. some of them non-zero while others negative or 0, so as to make this sum 0. And that means Vx can be 0 at some other locations also other than x equal to 0. And we see that even for negative values of x, if this sum is negative, then also its square will be positive, and so Vx will be either positive or 0 for different values of these x. So Vx is positive semi-definite function. This one we can convince ourselves that summation of x1, x2 etc. can be positive, can be negative or can be 0. So Vx acquires values which are positive, which are 0 as well as which are negative. So it is neither positive definite nor positive semi-definite nor negative semi-definite, and so it is indefinite. So having understood the definiteness of a function of vector x, we will understand quadratic form. It is very important in stability analysis and also in controller design. So it has this form. It is written as the vector x transpose into a matrix R into X. R is of course n by n matrix. It is a square matrix. And it is also a symmetric matrix. We'll see. When we expand, this X transpose is like this, and this X is this, and this R is written like this. So its various elements R11 etc. up to R1n, and similarly Rn1 up to Rnn. It is n by n matrix, as I said. So this R is like this, X transpose is like this, and X is like this. When we further evaluate this, this Vx becomes R11 into x1 square plus R21 into R12 x1 x2 and so on up to x1 xn, and then similar products. So what we see, it contains order 2. All the various terms have order 2. So this X transpose Rx is a scalar function which contains only second order terms in X. In other words, it is a homogeneous function of degree 2 in X, and this is a quadratic form. So quadratic form is a homogeneous function of degree 2 in X, where X is n-dimensional state vector. There are, for example, this is one example. This is written like this, and it can be written like this. This 2x1 square gives a 2 here, 2x1 x2 gives 1 here and 1 here. Excuse me. This 2x1 square gives a 2 here, x1 into x1. Then this 2x1 x2 gives a 1 here and a 1 here. Similarly, 4x2 square gives a 4 on this diagonal. This 5x3 square gives a 5 here. There is no term x2 x3, so this is having 0 here. And there is x1 x3 with minus 4, so minus 2 is here and minus 2 is here. So what we have done, we have written this as the product of X transpose Rx. However, we have made this R matrix in a symmetric fashion, a symmetric matrix, because only it is the symmetric matrix which is to be considered. It is only the symmetric part of R which is to be considered. We will see in the next slide, but let me make a comment here that definiteness of a quadratic form like this depends on the matrix R, this matrix R. So if R is okay, so first we see that symmetry, only the symmetric portion of R to be considered. So we know that Vx is a scalar function which is a product of X transpose R and X. It is also X transpose R transpose X because it is scalar. So it can be represented either by this product or by this product. If R is unsymmetric, then only the symmetric part of R needs to be considered, because if it is unsymmetric, then it can be represented as a sum of a symmetric and an unsymmetric components. Rs plus Rsk is skew-symmetric component. And in this Rs is given by this R plus R transpose half, and skew symmetric component is given as half of R minus R transpose. Now we see what happens when we expand this. Supposing that R is not symmetric, then it is sum of symmetric and skew symmetric components, RS plus RSK. We open this product, and so we get X transpose RSX and X transpose RSKX. And RSK, we substitute this one there, R minus R transpose divided by 2. This term is as it is. However, this term, the product is opened, so we have X transpose Rx minus X transpose R transpose X divided by 2. And we have seen that X transpose Rx is same as X transpose R transpose X. So these two will cancel each other, leaving X transpose Rx if R was unsymmetric as X transpose R symmetric X. So we need to consider only the symmetric part of R. R we can consider R as a symmetric matrix. We proceed with how to define. We proceed with how to define, how to test, know whether the R is a positive definite or not, how to decide its definiteness. As I stated here in this one, that definiteness of a quadratic form depends on the definiteness of matrix R. So how to know the positive definiteness characteristic of matrix R? So for this we apply Sylvester's theorem, and according to that, a matrix denoting a quadratic form is positive definite if all the determinants of principal minors of the matrix are greater than 0. So R was containing components like this. So this R11 should be greater than 0. This determinant formed by these four, R11, R12, R21, R22, that determinant should be greater than 0. Then this determinant formed by the R11, R12, R13, R21, R22, R23, R31, R32, R33, this determinant should also be greater than 0, and so on. The determinant of R, full R, also should be greater than 0. So if all n determinants formed by principal minors of R are greater than 0, then the matrix R is positive definite, or the quadratic form represented by that R is positive definite. If any of the above determinants fail, or if any one also fails to be positive definite, to be positive number by becoming 0 but not negative, only by becoming 0, then the quadratic form is positive semi-definite. If all are greater than 0 positive, then it is positive definite. If some of them or one of them becomes 0, then it is positive semi-definite. If minus R is positive definite, then R is negative definite, and if minus R is positive semi-definite, then R is negative semi-definite. So in order to test the negative definiteness, we have to test the positive definiteness of minus R by application of the Sylvester's theorem. So this is important. X transpose Rx, when the quadratic form is represented like this, then it applies to the whole state space. It is global. It is global. We have to keep it into mind. It is not confined to a part of the state space. As an example, we consider this R. We see that this is greater than 0. R11 is 2, which is greater than 0. We see that this part 2114, determinant of this is 7, which is greater than 0. And finally we see that the entire matrix R, determinant of that is 2 into 5 into 4, 20, minus 1 into 5, 5 minus this, so 1 into 5, and minus 2 into this one, 1 into 0 plus 2 into 4, so 2 into 8. This comes as 19, which is greater than 0. So we find that this is greater than 0, this determinant comes greater than 0, and the determinant of entire matrix comes greater than 0. So the conditions for positive definiteness are satisfied, hence R is positive definite. So in this manner we can determine the definiteness of quadratic form. As a corollary, we can see that if R is a diagonal matrix and if R diagonal elements are positive, all diagonal elements, then this matrix is positive definite. So a diagonal matrix consisting of all positive values on the diagonal is a positive definite matrix, and it is negative definite if all are negative, all diagonal elements are negative. It is positive semi-definite if some diagonal entries are greater than 0, positive, and some remaining diagonal entries are 0. So this R is positive definite, and of course negative semi-definite if all values are negative except some which are 0. Now another concept, which is simple closed surface. Now we saw the positive definiteness. So we have, let us say, a function Vx of vector x which is positive definite. In addition, what we are telling that there the norm x was limited up to k. Here it is approaching infinity. So if norm x is approaching infinity, because Vx is positive definite, Vx is expected to approach infinity. Then Vx equal to k and k greater than 0. So all set points which satisfy this Vx equal to k will form a simple closed surface. Closed surface and simple means the surface will not intersect itself. So Vx equal to k will form a simple closed surface. Anyway, we are seeing that Vx was k, but what is the difference? The difference is here. The difference is here that for x tending to infinity, Vx also is tending to infinity. So besides being positive definite, this is additional condition. So we expect that as x is larger and larger, the Vx will be larger and larger. And then Vx equal to k will denote a simple closed surface. And in addition, whenever k1 is less than k2, then that Vx corresponding to k1 will be inside the Vx corresponding to k2. So Vx equal to k1 lies entirely inside the surface Vx equal to k2. So of course in the two-dimensional space this picture is able to see, but in a 3 dimension and above we have to imagine that how it will look. But then Vx equal to k, whenever Vx tends to infinity, if x tends to infinity, and if Vx is positive definite, denotes a simple closed surface. So we consider this example with R equal to 1004, a diagonal matrix. So because this both diagonal entries are positive, this Vx is positive definite. It is easily verified. Now Vx equal to 1. It represents an ellipse described by this one. We can see that x1 square plus 4x2 square equal to 1. It can be rewritten like this. And Vx equal to 4. So x1 square plus 4x2 square equal to 4. It can be rewritten in this fashion. And if we plot this and this, we'll see that V1x is inside V2x. This will be V2x and this will be V1x. So this Vx, because for x tending to infinity, Vx is tending to infinity, this represents a simple closed surface in the form of that ellipse. Now we summarize what we covered so far. Of course, we only gave introduction to stability. We have not even defined the stability in the sense of Lyapunov. We only recalled some definitions of stability from the conventional control. But we have covered essential mathematical concepts which provide us footing for understanding the Lyapunov's stability. And these are scalar function of a vector, quadratic form, positive, negative, or positive semi-definite, negative semi-definite quadratic forms by use of Sylvester's theorem. We could determine the definiteness of quadratic form. We saw with example. And we saw that a quadratic form Vx less than equal to k, Vx equal to k, that set of points represents a simple closed surface if Vx is unbounded for x unbounded. Now with this mathematical foundation, we are ready to learn Lyapunov's stability. Thank you, and we meet again in our another lecture.